Okay, so the problem says a container holds 1.5 grams of argon at a pressure of 8.5 atmospheres. Okay, so how much is required to increase the temperature by 100 degrees Celsius at constant volume? Then the second part, part B, how much will the temperature increase if this amount of heat energy is transferred to the gas at a constant pressure? Okay, so let's talk about each of these. And let's write down what we do know. And this is going to be a little bit different than a solid or a liquid because we have a gas and we're dealing with gas inside of a container. All right, so our pressure is 8.5 atmospheres. And then our mass of argon gas is 1.5 grams. Okay. And then how much heat is required to increase the temperature by 100 degrees Celsius? I'm going to write that down. Delta T is going to equal 100 degrees Celsius. So let me show you what I have written down. All right. So here's what we know so far. We know the pressure, which is 8.5 atmospheres. We know the mass of the air, 1.5 grams. And we know delta T, which is 100 degrees Celsius. Now, what's really incredible that I think most people don't think about is that air actually has mass. Um, and the air actually has quite a bit of mass, right? If you've ever been scuba diving, that's when I first realized it because a scuba tank is significantly heavier if it's full than if you've been scuba diving. Okay, there's a big difference. That air actually has mass, and that's what the pressure is caused by in the atmosphere. So when we're sitting here, there are um, thousands of feet of air on top of us. Gravity is pulling all that down, and so that actually creates pressure here on the surface of the Earth. So air has mass and it's a pretty significant amount of mass. Okay, guys, the next important thing is we need to read the problem, and it says, how much heat is required to increase the temperature by 100 degrees Celsius at a constant volume? Okay, so that means that our the pressure is going to increase in this situation. Um, and our volume is not going to change. So the other constant that we're going to need to talk about is Boltzmann's constant. Okay, this is another very important constant that we're going to use a lot. Okay, and Boltzmann constant is equal to 1.380649 times 10 to the minus 23 joules per Kelvin. And this is a very important concept that we're going to use to relate the thermal energy in a gas to a gas's kinetic energy. Okay. And um, and we're going to use specifically this equation, and I think this is the equation we're going to use to solve this problem, which is thermal energy is equal to 3/2 times N times Boltzmann constant times T. And N is uh, the number of atoms that we're dealing with. Number of particles. And they're bouncing around. Okay, so let's zoom in here to the top of the can of the Pepsi. We're gonna zoom in here. I'm gonna draw a giant can of Pepsi down at the bottom of the page. Yes. Here's my can of Pepsi. Okay. We have the liquid Pepsi down here in the bottom. Okay, so here's my liquid Pepsi. The can the can is full of liquid Pepsi. And my cat is asking for some what? Well, let's imagine we have one Pepsi molecule, right? And before the sun starts shining, this thing is flying around. It's got some kinetic energy. It's gonna bounce off the walls, okay? This thing is kind of bouncing around. And it's not gonna do anything. It's not gonna spray boiling Pepsi on your car, okay? But let's say when you shine the sun on your car, okay, these atoms get a huge amount of thermal energy, okay, and their kinetic energy is very high, and so they go very, very fast. I mean, these Pepsi molecules are zipping all over the place, okay? Now, the pressure inside of a container comes from the air molecules hitting the sides of the container. So, what does that mean? Well, the hotter these molecules get, the more kinetic energy that they have. And they start striking the surface of this container with more and more force. Okay. And I drew them a little bigger because yeah, the electrons on the atoms are getting more excited and they're also getting more, their path length goes way up and they have very high kinetic energy. Okay. And in the book, okay, it talks about this equation right here. This is related to the kinetic energy. Okay. Another way we can write this equation is the thermal energy. The thermal energy is equal to the number of atoms times the average kinetic energy of those atoms. Okay. And it's the same thing. A way to calculate that is right here. Okay, so this is how we get the kinetic energy of our gas molecules. Okay, so what you could do is you could say, okay, what is the kinetic energy of my gas? I can just set these two things equal to each other. I'm going to say, okay, the number of atoms times the average kinetic energy is equal to 3/2 times n times Boltzmann's constant times T. Okay? Now, um, I'll talk about this equation a little bit here, but the number of atoms cancels out. Okay? And this is some really cool physics because what this is saying now, okay, is that the average kinetic energy of a Pepsi molecule in my car on that hot summer day that my wife never let me forget because my car was literally sticky for years, okay? So the kinetic energy is equal to 3/2 times KB times T. Now, where did they get this equation? Okay. How did we come up with this? Okay, because this is a very useful equation. Okay, we can do other things here. Let's say we want to find, well, okay, these molecules are zipping around in here. How do we find what their velocity is, right? How do we know how fast these things are actually moving? Okay, well, this is really cool. Okay, we're gonna say, all right, so this is equal to 1/2 times m times v squared, because that's our kinetic energy. Okay, so this means it's gonna be our average velocity, and that's gonna equal 3/2 uh, times kb times t. Okay, well, guess what? Now we can solve for our velocity of a single gas molecule. Okay, so I'm gonna multiply both sides by 2 here. Okay, my 2's are gonna cancel here. All my 2's are gonna go away. Okay, I'm gonna divide both sides by m. Divide this side by m. Okay, and I'm gonna take the square root of both sides, and so I'm gonna end up with here, after a little bit of algebra, it's gonna be 3 times kb times t over the mass of one of these molecules. Okay, so where are we at here in terms of the problem? Because that's what we're trying to figure out here, is we want to actually solve this problem. And we now have the equation to tell us how much thermal energy we need to supply to n number of gas molecules times Boltzmann's constant times the change in temperature here. So we'll call this delta T. Okay, here's the energy that we need to supply to our system. And remember, we're talking about a closed volume. Okay, so this is some container here that's full of ideal gas particles. Okay, and so these particles bounce elastically off the walls, and so here's the amount of energy that you need. But you're like, but Dr. Wisby, I, I have 1 point. What did it even say? Ah, yes, of course. I have 1.5 grams of argon. Okay, how many particles is that? How many particles is that? And what kind of question mark is that? Oh my goodness. Okay. Well, you know what? I'm so glad you asked that because now you have the ability. If I say I have 1.5 grams of argon, how many particles is that? I feel like I'm going to ask that on the test tomorrow. So I'm gonna do this problem on the test. Okay, so this will be. I'm gonna be. Yeah, this is gonna be on the. This is going to be on the exam. All right, so we know that argon is monatomic, and we're trying to figure out, well, how many gas particles do we have so we can use this equation up here. Okay, so um, now I'm gonna get in. Okay, did I already find n? Oh, I found in the number of yeah, that's the number of moles. Okay, I took the molar mass and I divided the mass of the argon that we had by its molar mass. Okay, this tells me in the number of moles. Okay, now, so what I'm gonna do here is I'm gonna say big N, okay, is equal to little n times big N, Avogadro's number. Okay, so I'm going to take the uh I'm going to take the number of moles and multiply it by Avogadro's numbers, and that's going to tell me how many particles I have. Okay, that's what I want. I want the number of particles. Okay, so I'm going to take my results and I'm going to say, I'm going to go up here actually. So I don't like to just multiply by the answers. I want to keep everything here in the same line so that I can go back and I can read it. So I'm going to type in Avogadro's number here, 6.022 times. Here, I'm doing scientific notation. 10 to the power of 23. Okay. And what do we get here? Aha. Okay, so this is the number of particles that I have here. Okay, so it's 2.261 times 10 to the 22nd. That's how many atoms I have. Okay, I'm gonna write that down here. Okay, so I have N, which is gonna equal 2.261, and I'll write down these other numbers. 0763 times 10 to the power of 22. That is the number of atoms that I have. So we have just figured out 1.5 grams of argon gas has 2.26 times 10 to the 22 argon atoms. And we'll say this is argon atoms. Boom. Okay, now we can plug all this in here. And it's getting a little crazy on my calculator. So I think I might throw this one into MATLAB. But you're like Dr. Wisby, I don't get to use MATLAB on the test. You know what? You're right. Okay, we'll put it all in here. You know what? I'm gonna go back up to this line. Okay, I'm gonna keep everything here. I got 1.5 divided by 3.95 times Avogadro's number. Okay, and then what do we got over here? All right, we figured out what n is. Okay, that's what we got right here. So now we need to add Boltzmann's constant. We'll put in the 3/2 times 3/2. Okay, this comes from the fact that it's an ideal gas. And we got to multiply by Boltzmann's constant, KB. KB, not Kobe. Okay, so we're gonna put this in. Okay. Boltzmann's constant, I wrote it down over here. It's 1.380649. I'm gonna keep all the digits in. Oh, and look what I did. Oh my goodness. I put an extra decimal there. I'm selling. Okay. 649 times 10 to the 23. 10 to the power of 23. Okay, what do I got here? And the temperature change, delta T. What did the problem say? The survey says, all right, way back when we were talking about this problem. Oh, it's 100 degrees Celsius. It's 100 degrees Celsius. Okay, we're gonna put in that's delta T times 100. Okay, let's just review here. I'll press enter. Okay. I got some kind of weird answer here. All right, what do we got here? 4.68 times 10 to the power 47. That is not right. I don't know what the heck. What did I do? All right, I feel like I forgot. Now see, the beauty of this is I know that this answer is wrong, okay? Because that answer doesn't make any sense, okay? It should be a number of joules. I'm thinking maybe a few hundred or a few thousand. Okay, I don't know what happened here. I'm gonna go back and I'm gonna look at this. Okay, I have 10 to the power of 23. Now the other one here. Okay, oh, there it is. This was supposed to be. Oh, first of all, okay, right here. This was supposed to be the power of 22, and then the ideal gas constant is the power of minus 10 to the 23. Okay, see, I kept all this in here. And see right here, this should be minus 23. So I'm going to press second insert. I'm going to try and put in a minus sign here. Boom. It did. Oh, it took it. Okay. Wonderful. All right. And now, am I still in insert mode? Oh, jeez. I don't know. Oh, no, I had. Okay. Let's press enter here. Okay. 46.8. That seems a little bit more reasonable. All right. Let's go through the math one more time just to make sure that we got it all. Okay, I think I had it, but I forgot to push record. So we put the numbers in here. We ended up getting 46.8 joules. We use this equation here. The thermal energy required to raise the temperature, that's delta T, is equal to 3/2 times n, the number of particles, times Boltzmann constant times the change in temperature. Okay. Um, right here, we used the fact that argon has a molar mass of 39.95. Okay. So then we said, all right, how many moles do we have? Okay, because we need to find out what N is. I don't know what N is. I don't know how many particles there are in 1.5 grams of argon, so we need to figure it out. Okay, we can get it from this equation right here. Okay, the number of moles is equal to the number of particles divided by Avogadro's number. Okay, and this mass here on the periodic table, that is the mass in grams of this element per mole. So 1 mole of argon weighs 39.95 grams. Okay, so we said we have 1.5 grams of argon divided by the molar mass, 39.95 grams per mole. Okay, that gives us 0.0375 moles. That's the number of moles that we had. Okay, then we use this equation right here. Okay, the number of moles equals the number of particles times Avogadro's number. So I multiplied both sides by Avogadro's number. Okay, so we had little n times Avogadro's number. Number of moles times Avogadro's number tells us the number of particles. Okay, so we had 2.26 times 10 to the 22nd argon atoms. Okay, so to get the thermal energy then, okay, it's 3 halves times the number of particles, n. 2.261 times 10 to the 22nd times the ideal gas constant, 1.38 times 10 to the 23 joules per Kelvin times our temperature change. So 100 degrees C. This is how much the temperature of our gas changed in this enclosed container. Okay. That gave us a very reasonable answer of 46.8 joules or 47 joules. When I first calculated this, I forgot the minus sign here on the ideal gas constant, which of course gave me an answer that was times 10 to the power of 46. That doesn't make any sense. I don't know if even the sun has that many joules in it at any given time. That's probably enough to melt the planets. I haven't done the math, but it seems a little bit high. Anyways, uh, back to my can of Pepsi here. So 47 joules is the number it would take to explode a can of Pepsi. Wow.
Thank you. Like and subscribe down below.